Hello, and welcome back to the MCAT grind. We have Physics Chapter 5, Electrostatics and Magnetism. We have here force, discussing electric field, electric potential energy, as well as electric potential. Give me 1 second. Now, if you need a refresher, we have a positive charge and a negative charge, a proton and an electron. Between them, you have a field lines going from positive to negative, and if you have multiple charges, then the positive charges will draw a field line towards the negative, and negative receives the field lines. The force is the one that's felt between them, the attractive force. Now, you'll find that the first equation describes the attractive force they feel for each other, and it consists of the Coulomb's number, 9 times 10 to the 29 newtons meter squared over Coulomb squared, multiplied by the charge of one and the charge of another over the distance r between them. Electric field, however, is at any point where the lines point from positive towards the negative. That's how the field works, how the field is oriented. Now, what the electric potential energy describes is the derivative. It's the antiderivative of force. So think about antiderivative is the area integrated under, and it is the energy or the work felt at that point in time, and the potential energy can be converted into kinetic energy. So if I drop a point charge between them, and let's say I move the positive and negative super far apart, this builds up energy, right? And when I let go, they'll come crashing together and start moving towards each other at a kinetic energy, right? I can use that to convert and find a velocity they will be traveling towards each other. You can also turn that into electric potential, which is at any point, if you place a point charge anywhere along this line, along the field line, how would they go ahead and travel? Which direction would they travel? Well, if you place a positive point charge here, then they will travel to a place with lower potential. Think about putting a ball on top of a hill. It's going to roll downwards, right? And what if you place something that floats underwater? Well, it's going to float upwards, right? That could be like a negative charge moving up the electric field towards the positive. So electric potential describes how much the object wants to go along the electric field depending on what charge they have. Now, we also have what's called a dipole moment that occurs when you have them bonded together. Think about if we have a hydrogen and an oxygen here, and of course the positive wants to orient itself to the electric field and moves towards that way, and the negative part will want to move towards this way, which is away. Now, what this looks like here is if I have positive on this side, negative on this side, it'll want to move like this. So it orients like so. What happens then is here it would experience no net force at this direction because it's already perfectly oriented. What we could use to calculate the dipole moment would be Q, the charge, as well as D, the distance. And what we have is force experienced by the push, and it is calculated by the charge multiplied by the strength of the electric field going through. The electric potential could then be calculated from the Coulomb's number times the dipole over r squared. If you notice, QD is substituted for P, and what we can here is extrapolate all the way out here. They're treated as a single charge of P, because if you observe from super far away, they have basically one small charge at this point. Just zoom out, they're basically collectively together. Now, what this also means is there's a torque because it's a rotational across the point, right? It's not moving unidirectionally. It's moving around the point. This torque is explained by the dipole multiplied by the electric field multiplied by the angle at which it's oriented. You'll get maximum torque, remember, when its field's going like this, where the force is exerted on, turning it this way, just like pushing the door this way along the field. Now, how do we derive this equation? Well, P is basically the same as QD. So if we were to leave Q over here and divide D over here, we have P over D equals Q. Same thing over here. E equals F over Q. Now, if we were to substitute P, QD over here and multiply F over Q into E, we have F times D times Q divided by Q. So that ends up with FD sine theta, which is the same as our original torque equation. Lastly, we have magnetism. Magnetism is defined as whether paramagnetic or diamagnetic material. Everything is either that, where electrons are paired together or they're isolated in the orbitals. If you recall from the orbital theory, you could either have one electron or two electrons for every little stage per the the Hans rule, where everyone wants to fill up a seat before two sits together. So if you have everyone sitting together, two every seat, then that's diamagnetic. Di, as in two. Paramagnetic just means there's a one for each of them. Now, diamagnetic materials include wood, insulators, because they don't participate. They don't have enough space, basically, to participate in magnetism. However, in paramagnetic materials, since they only have one, they can freely move about, and they're conductors like metal. And in regards to magnetism, is a combination of where electrons flow, wants to move about, in a current. So with a current running through a straight wire, there's a magnetic field unraveling through and around. If this is a wire carrying the current with electrons shooting through here, they expel out a magnetism going like this, looping around this way because of right hand rule. That's my thumb going in the current. This is how the wrap goes, the raveling of a field goes, and my middle finger will be on right hand rule, pointing to where the magnetism is going, and it's following along a loop, wrapping like so. However, if I have my magnetism on a loopy, the middle one will be where the magnetic field goes through, right through the center, and it's through 2r because it's only through the center, whereas magnetic field based on the area around the wire is based on 2 pi r, and the r is the distance of the loop away from the loop. Lastly, we have the force exerted by the magnetic field. You just input B into here, and on a moving charge, the faster it goes, the greater the force of the magnetic force it will exert. The Q, the charge, is also influenced, and of course on the sine theta, because it's a cross product between the magnetic field and how in which direction it's moving. If the magnetic field is more and more closer together to cosine, then that exerts a lot less product of the force. But if they're perfectly perpendicular, then that creates a huge net force. Then we also have a long loop wire, which uses BIL, sine theta, and depends on the current, size of the current, as well as the length of the wire. The longer it is, the more magnetic force is exerted. Alright, that's pretty much it for electrostatics and magnetism.